Now we turn to the big picture. Let's compare all these sorts side by side and look at the mistakes that bite you in C. This is the completed contract. Each row is one algorithm. The columns tell us if it is stable, if it is in place, and its best, average, and worst case cost. Insertion sort is stable and in place. Its best case is big O of n on nearly sorted input. Its average and worst case are big O of n squared. Selection sort is not stable, but it is in place. It is big O of n squared in every case, even when the input is already sorted. Merge sort is stable, but not in place. It guarantees big O of n log n in all three cases, at the cost of extra memory. Quicksort is not stable. It is in place, with a small star. Its best and average case are big O of n log n, but a bad pivot drops it to big O of n squared. Heap sort is not stable, but it is in place. It is the only algorithm here that is both big O of n log n guaranteed and in place. Now read that table backwards. Instead of picking an algorithm and looking up its properties, start from what you need. Memory type, then avoid merge sort because of its second array. Stability required, then insertion or merge. Need a worst case guarantee, then merge or heap. Quicksort cannot give you one. One footnote about Quicksort's memory. It needs no auxiliary array, but its recursion stack is not free. Big O of log n extra space on average, and big O of n in the worst case. These are the common mistakes in C. Each row gives the mistake, the symptom it causes, and the fix. Let's walk them one by one. The first mistake is quicksort with a fixed last element pivot on sorted input. The symptom is big, O of n squared time, and a recursion depth of big O of n that can overflow the stack. The fix is a median of 3 or a random pivot. The second mistake is assuming any sort is stable. The symptom is a secondary sort key that silently loses its original order. The fix is to use merge or insertion sort, or check the documented stability. Two more bugs. First, a merge sort that forgets to free the auxiliary array. The symptom is a memory leak on every single call. The fix is to always pair the one malloc with a free before returning. Second, and off by 1 in the partition bounds, high instead of high minus 1 in the scan. The symptom is that the pivot compares against itself, or one element is skipped entirely. The fix is to scan J from low to high minus 1 and place the pivot at high separately. This is a real measured bug. On sorted input with n equal to 8, Quicksort's last element pivot makes 28 comparisons and 35 swaps. That is its worst case. Every partition peels off only the pivot, so the recursion tree is one long lopsided line. And 28 is 8 times 7 over 2, the classic big O of n squared triangle. On random input of the same size, Quicksort makes only 14 comparisons and 9 swaps. A mixed order splits the array roughly in half on most calls. That stays close to the big O of n log n average. These counts come from this chapter's Lab 2 program. The fix is to pick the pivot as the median of the first, middle, and last elements, or to pick a random element. Either one breaks the always sorted input trap.